All right, today we're going to talk about the story of a true pioneer in artificial intelligence, the deep belief network. And look, this isn't just some dry algorithm, it's the story of a breakthrough idea that basically unlocked the door to the entire deep learning revolution we're living in right now.
So, to really get why deep belief networks, or DBNs, were such a huge deal, we have to ask ourselves a pretty basic question. How did deep learning even learn how to be deep? You see, for a long time, just adding more layers to a neural network, well, it didn't work. It actually made things worse. So what changed?
Here's how we'll break it down. We'll start with the huge problem that was holding AI back. Then, we'll see how these belief networks came on the scene with a whole new plan, how they were built, what they actually did, and finally, why this pioneer story is still so important today. Okay, so let's set the stage. Way back, before the whole AI boom of the last decade, researchers were up against a massive wall. They knew, in theory, that deeper networks should be way more powerful, but in practice, they just couldn't get them to learn anything useful. You know, these early attempts at deep networks ran into a few massive problems. They were incredibly slow to train, they'd often get stuck in really bad solutions, but most importantly, they suffered from something called the vanishing gradient problem. And honestly, this last one, this was the real killer. So what exactly is the vanishing gradient problem? Well, imagine you're training a network. The error signal, that's the little piece of information that tells the network how to get better, it has to travel backwards through all the layers. But in deep networks, that signal would get weaker and weaker with every single layer it passed through. By the time it got to the early layers, it was basically just a whisper. It had vanished. And so those first few layers learned, well, pretty much nothing. The whole process just ground to a halt. And then 2006 happens. Jeffrey Hinton and his team published this paper that just changed everything. They introduced the deep belief network, and it wasn't just a small improvement, it was a totally new philosophy for how to train these deep models. So what is a DBN? Okay, at its heart is what we call a generative model. That means instead of just learning to, say, classify a picture of a cat, it learns the underlying patterns of the data so well, it could actually generate a brand new picture of a cat. And it does this by stacking simpler networks, and this is the key part, learning one layer at a time without needing any labels at first. Now, to really get how a DBN works, we've got to look at its basic building block. It's this surprisingly simple but really powerful little thing called a Restricted Boltzmann Machine. An RBM is just this little two-layer network. You've got a visible layer where you put your data in, and then a hidden layer that learns to spot features in that data. Its whole job is to take an input, break it down into abstract features, and then try to reconstruct the original input using only those features it learned. The secret is right there in the name, restricted. It all comes from one simple, powerful rule. Neurons in the same layer are not allowed to talk to each other. And that one little restriction, it makes the math so much simpler, which means RBMs are way more efficient to train. And this leads to the absolute core idea of the DBN. You just stack these RBMs. Once you've trained the first one, its hidden layer, which has now learned some useful features from the raw data, becomes the input for the next RBM you stack on top of it. It's like building a skyscraper one floor at a time. This whole stacking approach is what made the DBN's secret sauce possible. It's a really clever two-phase training strategy that just completely sidestepped that whole vanishing gradient problem. Okay, here's how it works. First, you have this unsupervised pre-training phase. You train each RBM layer by itself, one after another, just letting it learn the structure of the data you feed it. No labels needed at all. This process gives the whole network a massive head start. It's not starting from random. It already kind of understands the data. And only after all the layers are pre-trained do you get to phase 2, supervised fine-tuning. That's when you bring in your labeled data and use good old backpropagation to just tweak the entire network for your specific job, like image classification. Now, the engine that powered this whole pre-training phase was a really efficient algorithm called contrastive divergence. It gave everyone a fast, practical way to get each RBM trained up, which was absolutely essential for building the whole deep stack. So this wasn't just some cool idea on a whiteboard. DBNs made a huge splash in the real world, and they were quickly put to work on some seriously hard problems. I mean, people started using them for all sorts of complex stuff. They were fantastic at image and speech recognition, they could analyze video, motion capture data, and were even used for things like drug discovery.
Their knack for learning features from unlabeled data made them incredibly versatile. And just to give you a sense of the kind of heavy lifting these models could do, think about this number, 65 terabytes. So where does that crazy number come from? NASA. A team there used DBNs to process a massive 65 terabyte dataset of satellite images. For that time, this was a mind-boggling amount of data. And it was the DBN's smart layer-by-layer training that made it possible to find useful patterns in all that noise. Okay, so if these things were so powerful and they solved this massive problem, that leads to a pretty obvious question, right? Why isn't deep belief network a household name today? Let's just ask it directly. What happened? Did they turn out to be a dead end, or did something else just come along and steal the show? Here's the most crucial point. DBMs were an incredibly clever workaround. That whole layer-by-layer pre-training thing was a genius way to give the network a good starting point, so the training signals wouldn't die. But then, just a few years later, researchers found a more direct solution. Things like the ReLU activation function came along, and they just solved the problem. They kept the gradient signal strong from the get-go, which meant that whole complicated pre-training process just wasn't necessary anymore. But listen, this does not mean DBNs were a failure. Not at all. They were an absolutely crucial stepping stone. They deserve a spot in the history books because they proved for the very first time that, yeah, deep networks could be trained effectively. And that proof of concept is what kicked off the entire deep learning revolution that followed. And that leaves us with a pretty fascinating thought. The story of the DBN is just a perfect example of how science moves forward. It really makes you wonder, right? Which of the cutting-edge breakthroughs we're all so excited about today are actually just the DBNs of our time, the clever pioneers, the crucial workarounds that are just waiting for a simpler, more elegant solution to come along and take their place?